This
operations
conference
management
will now be
problems.
recorded.
So operations management problems. Now, if you look at operations management problems, mostly the operations management problems are combinatorial automation problems. You talk about assembly line balancing problem or say facility layout problem. So mostly it is a combinatorial automation problem. So the first thing that I want to differentiate, what is the what is the what is a combinatorial optimization problem? Now, if you think of any optimization, you will have a objective function, either maximize or minimize, subjected to some constraints. Now, if you have fx is the objective function, where x is a vector of decision variables, x1, x2, x3, all the decision variables. Now, our objective is to find out the best values of these variables x1, x2, all that, so that the objective function will be either maximized or minimized. Now, in that case, the values of x1, x2, x3, all these are in continuous values. Okay, either it may have floating point variable or it may be discrete or integer variables. Mostly it is like this. Now the question arises, what is combinatorial optimization problem that will really apply to operations management problem? Now generally in operations management problem, we come across the problems like assembly line balancing, scheduling problems, traveling salesman problem, vehicle routing problem, um, the loading problem in FMS loading problem, scheduling problems. So all these are, or say, cell formation in group technology, cellular manufacturing, cell formation, machine cell formation. All these are combinatorial optimization problems. Combinatorial optimization problem, I mean, you find the combination of the of the of the things that is to be performed. For example, you take a simple flows of scheduling problem. Now, in a flows of scheduling problem, you have several machines and you will have jobs. Suppose you have 5 jobs. These are to be processed on 3 machines, machine 1, machine 2, machine 3. Now, operation time of each job on each machine is different. You will be given the operation of job 1 on machine 1, operation of job 1 on machine 2, operation time of job 1 on machine 3. Similarly, for job 2, you will have the operation time on machine 1, machine 2, machine 3. So this is a simple flows of problem. In this flows of problem, we have to solve it using a method known as Johnson's rule, or that is a heuristic method. So what we suppose 5 jobs are there, what you are finding out that what is the combination of the jobs that is to be processed in all the machines so that your completion time will be minimum. Completion time of all the 5 jobs will be minimum. That is what our objective is. So since you have given the processing time on each machine, the jobs, and a job cannot jump or avoid any processing on the machines. All the jobs will be processed in a similar fashion in all the machines, or each job will be processed on 3 machines. That is what the condition in a flow job. So, hello.
हेलो
Yes.
सर सर गुड आफ्टरनून मैं अरविंद झा बोल रहा हूँ एग्जीक्यूटिव पीएचडी स्टूडेंट इस साल एडमिशन लिया
थोड़ा बाद में बात कीजिए, मेरा थोड़ा काम चल रहा है अभी। हाँ
ठीक है सर 2 बजे करूँ सर
हाँ हाँ ठीक है।
ठीक
So, these are
Sir,
the
excuse me, sir.
yes.
Sir, your
Yes.
presentation is slide is not in presentation mode. It is in the first slide only.
Okay. Yes, I have not. I have not gone to the second slide.
Okay, okay.
Still in the
Okay.
still in the first. So
Okay, sorry, sir.
what? Okay. So what is the thing is that in a process of scheduling problem, we have to find out a combination of the jobs so that the we will process the jobs in such a manner that the completion time of all the jobs will be minimum. Okay. So this is what the condition. Now here, since you are having 5 jobs, you can have factorial 5 combinations. 1, 2, 3, 4. That is one combination. 2, 1, 3, 5, 4. That is another combination. So similarly, you have, if you enumerate what type of the combinations that will come, there will be 105 factorial, 120 combination. Out of that, one will be the best. If you have 10 jobs, then there will be 10 factorial. So it is really time consuming to solve such type of problems. So what we do here, we find some heuristics or meta heuristics to solve such type of problems so that the computation time can be minimized. This is what we do. If you talk about the assembly line balancing problem, we have a similar problem. In the assembly line balancing problem, we assign the task to different stations. Assign the task to different stations. So the combination of the tasks to be assigned in the different station. So we have to find out what are the combination of the tasks to be assigned to different stations in an assembly line, so that your um, line efficiency will be improved, or the smoothness index will be minimized. This is what we do in the assembly line balancing problem. And similarly, if you talk about the, yes, if you talk about the layout planning problem, there is one algorithm that is known as the craft algorithm. In the craft algorithm, that is used in the process type of layout. So where we can locate the departments, lathe department, milling department, where we should locate, or what is the best combination of the location of the department, so that we can achieve some advantage or efficiency can be improved. So these are the different types of problems where the combination is very important. And generally, when you talk about the combination, finding out the combinations in different types of operations management problems, we generally talk about the NP hard problems, non-polynomial hard problems. Non-polynomial hard problems, I mean, when the size of the problem slightly increases, the computation time exponentially increases. These are called NP hard problems. So these are really difficult problems to solve, whether it is a line balancing problem or layout planning problem or sequencing problem or scheduling problem, whatever may be the problems where you are talking about the combinations, these are really difficult to solve. So that's why what we do here, we find out the what we do here, we talk about many types of heuristics. Heuristics are nothing but computerized thumb rules. So we say Johnson's rule in flow of scheduling problem case. That is a thumb rule. There is no mathematical or scientific proof of that, but the method works. So these are workable solutions. They give near optimal solutions, and these are working solutions. Similarly, if you solve the assembly line balancing problem, say largest candidate rule, largest task time, that rule, or the rank positional weight methods, these are the different type of heuristics we apply. These are nothing but the thumb rules. So what is the difference between a heuristic and the meta-heuristic is that the heuristic is developed, the thumb rules are developed to solve a particular type of problem. Say Johnson's rule, which is applied to close-up scheduling problem that cannot be applied to assembly line balancing problem or any other problem. Say in assembly line balancing problem, we use the rank positional weight method that cannot be applied to scheduling problem. These are the so heuristics are developed depending on the type of the problem. So in one problem, you develop a heuristics. But meta heuristics are generalized heuristics. These are mostly inspired from nature, and the heuristics have been developed. These are general purpose, and that can be applied to different type of problems or combinatorial optimization problems. So what are the meta heuristics that we come across these days? The meta heuristics, the best meta heuristics or technique is the genetic algorithm. Then particle swarm optimization. Then artificial immune system. So uh, and teaching learning based algorithm, TLP algorithms. So these are the meta heuristic algorithms which are quite general, and that can be applied to different types of problems. So first we will talk about the uh, genetic algorithm, and I shall give a basic idea in the continuous format of the genetic algorithm. Then we shall come to the combinatorial uh, type of the genetic algorithm. So you may have some idea on genetic algorithm. Genetic algorithm is based on Darwin's theory, that is the survival for the fittest. So in genetic algorithm, we artificially create the solution or randomly create some solutions, and the then you take two parents or two solutions, then then uh, cross over them, so they will produce two offsprings. Now these offsprings, if they are superior or better than the parents, they will survive or they will die out. This is what we do, survival for the fittest. uh, so to solve to solve any problem using genetic algorithm, we need three types of operators, that is reproduction, crossover, and mutation. Now first what you have to do for a problem, um, uh, you have to the variable bounds, what are the variables that you are having in the problem, these bounds should be known to you. Once you know these bounds, then you express these variables in terms of binary. So an example is given, how do you express a number into binary form. So so this is one simple hand computation by which genetic algorithm works. Now here the problem is to maximize a function fx is x square. Now there is only one variable, and x is allowed to vary between 0 to 31. Now first we have to convert this variable uh, in binary form. So and how many binary digits that will be required, it depends on the accuracy. Now 0 can be expressed in binary form 0000 like this. So these 5 binary digits express 0, and 31 can be given as 11111. So initially, for hand computation, for simple computation I have shown you, you initially generate these solutions or the value of x in the randomly you generate having five digits. So for four binary strings have been generated. Four binary strings. This four is known as the population size or size as the population. So 0, 1, 1, 0, 1. That will, this is in the binary, that is 1 into 2 to the power 0 plus 0 into 2 to the power 1, 1 into 2 to the power 2, then 1 into 2 to the power 3, then 0 into 2 to the power 4. So that will give you 13. Value of x is 13. And our fx is x square. So it gives you 169. Now out of these 4, in the next generation, what is the probability that they will survive or anything will perish? That we have to see. So that is known as the reproduction. So we have found out first one. For the first string 13, 169. Second string is value is in the decimal equivalent value is 24, that is 576. Then the third integer value, that is 8, that is 64. Then fourth, that is 19, 361. Then you calculate the sum of these all these x square values are written here for this population. It is 1170, and the average value is 1170 divided by 4, 293, and the maximum value is 576. Now calculate the probability of selection. Probability of selection is nothing but selection to the next generation. So it is nothing but 169 divided by 1170. It is fx divided by the summation of fx. So summation of fx is 1170. So 169 divided by 1170. So 0.14. Then 0.49. 576 divided by 1170. 0.49. 64 divided by 1170. 0.06. 361 divided by 1170. 0.31. That will find. Then also we calculate find out the expected count. Expected count is nothing but 169 divided by the average value, or simply you multiply this probability P select, probability of selection 0.14 multiplied by 4, because the population size is 4, so it is 0.56, or 0.49 multiplied by 4, that is 1.96, 0.06 multiplied by 4, that is 0.24, and 0.31 multiplied by 4, that is 1.24. So this is the expected count. So when the expected count is here, uh, the first string has a value expected count of 0.56. So that is one copy of this string will be taken to the next generation. So we have actual count we have given 1. Then this is 11000. This is the string. It has got the expected count of 1.96. So it is nearly approaching 2. So we have written 2. So 2 copies. Since this is a better solution, it is a maximization problem, and we have got the x square value is 576. So better solutions will be multiplied copies will be going to the next generation. So we have taken 2 copies of the string 2 or population member 2. Then third is it is one of the worst population, so that is not to be taken to the next generation. And fourth string to be taken 1 copy. So total 4 that population size is to be maintained. So when you are copying, you have to look at same population size must be copied to the next generation. Then you look at here, you see 1 copy of the first population member 01101, that is come here 01101. Then 2 copies of the second member 11000, 113, 0 0 0 and 2 copies of here 1 1 0 0 0. Then for the fourth one copy 1 0 0 1 1 1 0 0 1 1. Now after that you make crossover. Now crossover, you see, we have taken first two parents and then crossed it over. So this is the crossover site we have randomly selected. This is what the crossover site we have selected. So what we are going to do, that is 0 1 1 0 1 and 1 1 0 0. So the information beyond this line, this crossover point, that is exchanged beyond this line. That is, so what the first string after crossover, it becomes 0 1 1 0 0, that is 0 1 1 0, and the information from here. So 0 1 1 0 1, then second string becomes 1 0 0 1 1 0 0 1, and this third and fourth population members or the chromosomes, they have the crossover point is this. So information beyond this point is exchanged. So the third string becomes 1 1 0 1 1 1 1 0 1 1, and the fourth string becomes 1 0 0 0 0 1 0 0. You see the x value previously we had 13 24 8 19, and now it has got 12 25 27 16. So it is gradually increasing, and this is the sum value, average value, and the maximum value that we have found out for x square fx. So this is a very simple way of understanding the genetic algorithm, which is a metaheuristic which will be applied to operations management problems. And this is the crossover and the um, reproduction, crossover reproduction from this population, it has gone to the another generation. Then the crossover, I have shown how the crossover is being made, and once the crossover is made, then we do the mutation. Mutation means randomly choose a point where 0 will be changed to 1 and 1 will be changed to 0. That is what the mutation. Mutation is nothing but the fine tuning. So the standard genetic algorithm talks about you generate the initial population assay, evaluate the population assay. While stopping criteria not satisfied, repeat, select the elements assay to put into SA plus 1, the string SA plus 1. That is the you generate assay and put in SA plus 1. Then the crossover element assay and put it into SA a plus 1, mutate SA and put in SA plus 1, evaluate new population SA plus 1, then make it SA equal to SA. This is the standard genetic algorithm. We do SA is nothing but the set of the strings. So normally we use a roulette wheel selection. In the roulette wheel selection, we have seen the roulette wheel roadside, you might have seen. So the better population has a larger probability of being selected to the next generation during the reproduction phase or reproduction, even you use the reproduction operator. This is what the roulette wheel selection. So better population are to be copied. Then this is another example is given, and here when you go for the reproduction, you see better you have omitted 6 and 7. These strings are omitted, and 2 copies of string 4 and 5 has been taken, and 1 copy for the others. And 6 and 7, they have worse solutions. They are removed from there, and when you go to the next generation, but the population size of 8, that is to be maintained. Now what happens, If you use a roulette wheel selection, there may be stagnation or diversity of the solution that may be losing. That's why there is another way of doing the reproduction that is known as the tournament selection. During the tournament selection, we choose two members of the um, two members and make a game between them, and the better one will be selected in the next one, or the winner will be selected to the next one. So suppose these are the individuals, a population, and the fitness function is like this, and randomly select two. Suppose two member 2 is selected, then string 3 is selected, then 2 is having the fitness function value or the objective function value of 2.1, and 4 is having 4.01. So 4 is to be selected next. 4 is better chance of getting selected. So similarly, we make game between or select two members and compare them and get it selected. Doing so, you see, string number 1 or population member 1 and 7 have been omitted, and 2 copies of 4 and 8 have been selected, and 1 copy of the others, and the new population is shown here. This is what we do. And there are many more type of selections. Rank selection, other method of selection is there, and these are the crossover. We select a crossover site and make the exchange the information. This is a single site crossover, this is 2-point crossover, uh, 2-point crossover, this is multi-point crossover. So many type of crossover is there, and this is a uniform crossover. Uniform crossover, uh, in the uniform crossover, you randomly generate a crossover mask and select parent 1 and parent 2. Now when in the crossover mask 1 appears, you select the information from the first parent. If 0 appears, we select the information from the second parent, right? So the crossover mask here is selected 10010111001. Parent 1 and parent 2 is there. Now when the offspring, what will happen? 1 is appearing in the crossover mask, so the information from the first parent is to be selected, so 1 is selected. Then 0, next digit is 0 in the crossover mask, so the information from the second parent is to be selected, so 1 is selected. Then here the again 0, so information from the second parent is to be selected, that is 0. Then 1 appears here, so information from the first parent is to be selected. So similarly, we select like this based on the crossover mask, so one offspring is to be and here offspring 1 is generated. Similarly, offspring 2 can be produced. So this is a uniform crossover, and the mutation once complement operator, that is select randomly a, a, a randomly select a position, and when 1 is there, you make it 0. When 0 is there, you make it 1. This is what the mutation you do. This is 5. As far as your objective function is continuous, or the values of decision variables x1, x2, x3 are continuous values, then you can use these whatever I have suggested, the crossover, mutation, all these can be applied. But when they are in combinatorial nature, it is not to be applied. So although in genetic algorithm we use 3, that is the 3 operators: reproduction, crossover, and mutation. Reproduction is nothing to do, you can use the roulette wheel selection or rank selection, because it is based on the fitness value or the objective function value. But when you talk about the um, um, when you talk about the crossover, it is not possible. So what you have to do when there is a combinatorial optimization problem? For the combinatorial optimization problem, different types of crossovers have been developed. Here one is the partially mapped crossover or PMX crossover is. This is known as PMX crossover or partially mapped crossover. Here what you do, suppose the parent 1 and parent 2 is there. I have told you that it is the your objective is to select the combination whether you apply to group topology problem or to assembly line balancing problem or facility layout problem. Here we are or scheduling problem, we are finding a combination of the jobs or combination of the departments or combination of the parts or combination of the machines. So this is what we do. So in the combination, when you look for the combination and do the crossover, what we do here in the premix crossover, suppose parent 1 is 1 2 3 4 5 6 7 8 9, p2 is 4 5 2 1 8 7 6 9 3. Now we want to produce some offsprings from that. Now you choose the crossover points. Okay, so two crossover points have been chosen. So now to the for the offspring, whatever found, this is the crossover point. This is the after third point, third digit, and then after 7 digits. Okay, so these are the crossover points. So whatever between these information between these crossover points, the information is exchanged. So what we have exchanged here, that is the in the first offspring 1876 and in the second offspring it is 4567. So now we have to make a mapping that 1 with 4, 8 with 5, 7 with 6 and 6 with 7. Now look at the first one, 1876. So here, since within these closed um, uh, closed lines, 2, 3 and 9 is not appearing, so we place them as they are. 2, 3, 9, we place them as they are, and this is not to be placed yet. So this point, and similarly here for the second offspring 4, 5, 6, 7 is already that is in the within these bounds. Now 2, 9, 3, they are not appearing in this in these lines, within these lines. So they have been placed as it is 2, 9, 3, and these points we have not placed so far. Now we look at for the first offspring, this vacant position. This vacant position in the original, in the parent, it is 1. Okay, so 1 is mapped to 4. So you can put here 4. Then this is a vacant position. You look at in the parent, what is the number? That is 8. So 8 is mapped with 5. So we put here 5. If you don't do this, then the numbers will be repeated. You will not get a good combination. Numbers will be repeated. So that's why you have to follow such type of rules. For the second parent, second offspring, 4, 5, 6, 7 is there. And what are the vacant positions? 1, 2, vacant position is there. So look at here for the second parent. So 4 is there originally. So 4 is mapped with 1. So put here 1. Then for the second, in the second parent it is 5. So 5 is mapped with 8. So put here 8. So we got offspring 1, 4, 2, 3, 1, 8, 7, 6, 5, 9. Offspring 2, 1, 8, 2, 4, 5, 6, 7, 9, 3. This is what a partially mapped crossover. Similarly, you can have a order crossover or OX crossover. It is known as OX crossover, order crossover. Now here The same, the two parents have been taken, P1 and P2, and we have taken crossover sides. Now, in the crossover side and other points, you keep a dot like this. Now, come to the first offspring. Now, we write for the right parent 2 in the reverse order, that is 9 3 4 5 2 1 8 7 6. Now, remove 4 5 6 7, which is already existing in offspring 1. So from this string, this combination, we remove 4 5 4 5 and 6 7 have been removed. So once you remove 4 5 7 6, then what we will having? 9 3 2 1 8. 9 3 2 1 8. So 9 3 2 1 8 is there. So we write 4 5 6 7, then 2 1 8 from the end, we write 2 1 8 here, and 9 3 you can write here. So this is what the OX crossover. Similarly, O2 can be found out from the P2. Okay, there is another important crossover that we find is the position based crossover. In the position based crossover, suppose these 9 points are given, it is written J1, J2, J3 like this. Basically 1, 2, 3, 4. To represent properly, I have written J1, J2 like this. So J1, J2, J3, J4, J5, J6, J7, J8, J9. Now, out of this, we randomly select some positions which are not going to be changed in the next in the offspring, which are not going to be changed. So what we have done is that we J1, J3, J4, J6, J8 we have underlined, we have selected 5, and they are not going to be changed. Now whatever have been selected here, their position is not going to be changed, that we have underlined, that has to be removed from the second parent, or these are to be highlighted in the second parent. So now what will be happening? To write J1 here, then J2, J3, J4, these positions are not going to change, and J5, for J5 you write J9. Okay, from here, from the second parent, J9. We are concerned with the J2, J9, J7 and J5 because these are not selected. These positions are to be changed, and these positions are not selected in P1. So in the P1, J1 position is not to be changed, J3 is not going to be changed, J4 is not going to be changed, J6 is not going to be changed, J8 is not going to be changed, and that we have underlined, that we have highlighted in the parent 2. What are the rest is left? So J2, J9, J7 and J5. So you fill in these blanks. Okay, so that is what a position based crossover, which is widely used. Then there is a position based mutation in which the position have been exchanged. Here J1 to J1, J2, J3, J4, J9 or to J5 is there, and J and when you change a position, randomly select a position, and say J8 is selected, and that is brought to here in the position of 2. So that has been brought here, then other has been forwarded. So this is the position based mutation. So these are the mutations and the crossovers that we have to use when there is a combinatorial optimization problem. That is essential. Without this, it may not be useful. So now thing is, how do we apply these things? Let us first come to a group technology problem where we can apply genetic algorithm for machine cell formation. Now, group technology comes under a layout planning which lies between a process layout and the product layout or the line layout. In the line layout, your product variety will be very small, but the production quantity or production volume will be very high. In contrast, in jobbing shop or in the jobbing shop industries are organized or layout is planned as per process layout. So in the process layout, the similar machines are grouped together. So there will be one lathe department, one milling department like this. Now, in that case, we will have more variety of production, but less volume of production. In between these two, there lies a technology or layout planning that is known as a group technology or cellular manufacturing. In cellular manufacturing, in olden days it was called group technology. So in the cellular manufacturing, what we do, we find the part families. Part families are the set of the parts which have more or less similar design and manufacturing attributes. So we find a set of parts or part family and arrange the machines to manufacture that part family. So that will give rise to a machine cell. So to do this, we have three types of methods to get the group technology. We have three types of methods. One is the visual inspection methods. In the visual inspection method, you go through the drawings of all the parts, then find out a part family. Or there may be part classification and coding system like Optis coding is there. So use that coding system and code the parts so that a part family can be produced. Once a part family is produced, assign the machine to produce that part family. Okay, so this is a coding and classification system that can be used. And another type of thing that we can do for simultaneously finding out the machine cells and the part family, that is using the production flow analysis. In the production flow analysis, we find an incidence matrix. If a part visits a machine, in that matrix, in that element or in that cell, we put an element 1 if a part visits a machine. If it is not visiting a machine, then we put 0. Now, how that information is obtained? Normally, all the jobs that is moving on the shop floor, they have got all the jobs, they have a root sheet. So in the root sheet, the information will be mentioned. What are the sequence of operations and on which machine that particular operation is to be carried out? All these things will be mentioned. So from that we can know whether a part is visiting a machine or not. For example, you find out here, suppose there are 7 parts, P1, P2, P3, P4, P5, P6, P7, and the machines are M1, M2, M3, 6 machines are there. Now you see here, the part 1 is visiting machine 1, only machine 1. So only one operation is needed of part 1, that is on machine 1. Part 2 needs operation on machine 2, machine 4 and machine 6. We are not telling what is the sequence of operation, whether first operation is on machine 2, then machine 4, then machine 5. We are not telling like this. Only this matrix, this is known as an incidence matrix. This incidence matrix gives the information that a part is visiting a machine or not. If a part is visiting a machine, then we put 1. If it is not visiting, then we put 0. Right? So, and the information is found from the root seeds of the jobs or the part. So, part 1 is visiting machine 1, so we put 1, others are 0. And part 2 is visiting machine 2, machine 4, and machine 6. So, here 1, 1, 1 we have given, and the others are 0. Part 3 is visiting machine 2, machine 4, machine 5, and others are 0. So similarly, all the parts visiting the different machines we have written. Now, we use a heuristic method known as rank order clustering, where you can find out the machine cells and part families simultaneously. This was developed by J.R. King in 1981. So this is known as the rank order clustering. So what we do here in the rank order clustering, you read each row as a binary word. You read each row as a binary word. Then write down its decimal equivalent. So the first row will be read as 1, 0, 0, 1, 0, 1, 0. Its decimal equivalent will be 74. Like 0 into to the power 0, 0, 1 into to the power 1, 0 into to the power 2, 1 into to the power 3, 0 into to the power 4, 0 into to the power 5, 1 into to the power 6. So it is total value is 74. Similarly, you read each row as a binary word and write down its decimal equivalent. Now once you find out the decimal equivalent, you arrange the rows as per the descending order of their decimal equivalent. So here we have arranged all the rows as per the decimal in the descending order of the decimal equivalent. So what will happen? First M1 row will come first, then M2 row, then M4 row, then M6 row, then M5 row, then M3 row, like that. Okay, so you see M1, M2, M4, M6, M5, M3 is written. Okay, it is written like this. Then after doing this, after arranging the rows, then you arrange the columns. Arrange the columns. So read each column as a binary word. So that is 1, 0, 0, 0, 0, 0. For the first column 1, 0, 0, 0, 0, 0. So you read this as a binary word. So the first column gives the binary equivalent, decimal equivalent 32. Second column gives 28, and third column gives 26. Like that you read this. Now arrange the columns as per their binary their decimal equivalent. So first row 4 comes column 4 comes first, then column 6, then column 1, like that. Okay, so this is column 4, then column 6, column 1, then column 2, column 3, column 5, column 7. Then after doing this, then again a row reordering and a column reordering makes one iteration. So this iteration is to be repeated till you get the part families and the machine cells. So again you read each row as a binary row and find out the decimal equivalent, and arrange the rows in the descending order of their decimal equivalent. Similarly, you take the columns and read each column as a binary word and arrange the columns. Once you do that, after 2 iterations, it will show that all the ones will be clustered in these major blocks. You see this red area. So you see all these ones will be clustered in these some major blocks, always in these diagonal blocks, always. Okay, in these major blocks. So if you say that there will be a part family having part 1, part 4 and part 6, and to manufacture this part family we need two machines, machine 1 and machine 3. So we have got a part family and a machine cell having machine 1 and 3. Then there is another part family having part 2, part 3, part 5, part 7, and the machine are M2, M4, M6 and M5. So this forms a machine cell and this forms a part family. So we will simultaneously get two part families and two machine cells, right? So this is a way we can get the using the rank order clustering, we can easily get the part families and the machine cell using the production flow analysis or the information available in the root sheet that is converted into the um, part machine incidence matrix. Then using row row ordering and the column ordering, we can get the disjoint block diagonal structure in the matrix. These disjoint block diagonal structures build the part families and the machine cells. So once you do this, there is another method that is known as a bond energy method. In the bond energy method also, a similar logic is being followed. What you do here now, first, what is the bonding between two columns or the two rows that is to be found out? If they are closely bonded, they will be in one block, right? So what we find here, you see there are 5 machines, 5 rows and 4 columns for the parts. Now first we make the arrange the columns. For arranging the column, we randomly select a column. So we selected a column 3 randomly. Selected column 3 randomly. Once you select column 3 randomly, then to find out what is the bond energy or bond energy between other columns. So column 3 with column 1, column 3 with column 1. The bond energy is nothing but the dot matrix of two columns. Dot multiplication, dot product of two columns. So if you multiply column 1 and column 3, dot product 1 multiplied by 1 plus 0 multiplied by 0, 1 plus 1 multiplied by 1 plus 0 multiplied by 0 plus 0 multiplied by 1. So it gives 2. 2 is written here. Then 2 with 3. 2 with 3, if you multiply, then it gives 0. 0. And 3 with 3 is not required because randomly we have selected 3. Then 3 with 4, so it gives 0. So now the column having highest bond energy, that is to be selected. So column 3 is selected randomly. Then with column 3, column 1 is having more bond energy. So column 1 is selected. So 3, then column 1. Then you with column 1 you calculate the bond energy with column 3. Column 1 with 3. Column 1 with 3. So 1, 1, 1, 0, 1, 0. So column 1 with column 3. since column 1 is selected, so we need not to calculate. So here column 1 with column 1 with 3, so that is to be found out with the column 2 and column 3. So column 2 is selected, then similarly you find with column 2 and column 4 will be selected. So 3 1 2 4 is selected. That is, so 3 1 2 4 will the rearrangement of the columns. Similarly we do it for the rows. Now there are 5 rows. Randomly select a row 1, then row 1 with other rows, calculate the bond energy, then row 3 with others. So like that you calculate the bond energy and select the row when there is highest bond energy, then rearrange the columns. So sorry, rows. So rearrangement of the columns is 3 1 2 4. Rearrangement of the rows will be 1 3 5 2 1, and you see all the ones have been arranged here or blocked here in block diagonal structures. So this is a bond energy method which can give you the simultaneous generation of the machine cells as well as the part families. And then the rank order clustering has been improved little bit again by J.R. King, and that has been improved. And improving this, we what is the advantage? And under that improvement, it is called rank order clustering 2. So using this, if block diagonal structures exist with the machines, exist with the matrix, then it can immediately give you the block diagonal structure with one iteration. So to explore that idea, we have demonstrated a small example here. Now suppose there are 7 parts and 5 machines. Now what we do here, you take column 7, okay, and make a row list here. Column 7 and row list is, that is row 1, row 2, row 3, row 4, row 5, that we have written 1 2 3 4 5. Now look at column 7. Whenever ones appear in the rows in that column, you underline here. So for column 7, row 3 and row 5 is having cell entries of 1. So underline that. So row 3 and row 5 have been underlined. Now when you underline them, bring them front, bring forth. So 3 and 5 when brought here, then and write others as it is 1 2 1 2 4. Then look at column 6. In the column 6, row 1 and row 4 is having ones. So row 1 and row 4 have been underlined and brought them back. So we have written 1 4 3 5 2. Then go to row 5. In the row 5, sorry, column 5. In the column 5, only row 1 is having 1. So row 1 is underlined. Then it becomes 1 4 3 5 2. Then go to row 4. In the row 4, sorry, column 4. In the column 4, row 1 and row 4 is having ones. So row 1 and row 4 have been underlined, and they are already in the front, so we need not to print. So write 1 4 3 5 2. Then go to column 3. In column 3, row 2, row 3, uh, they are underlined because they are having ones, so they have been underlined and brought them back. So it becomes 3 2 1 4 5. Then go to column 2. Here row 1, then row 4. is having. So bring them front. When you bring them front, then you go to um, column 1. So row 2, row 3, and row 5. Row 3, row 2, row 5. They have been underlined. So your new row order becomes 3, 2, 5, 1, 4. So your new row order becomes 3, 2, 5, 1, 4. 3, 2, 5, 1, 4. So they have been written 3, 2, 1, 5, 4. 3, 2, 5, 1, 4. And the columns remain same because we have not done anything with the columns. Then again do the column reordering. So start with uh, row number 5, that is the last row number 5, and take the columns. Columns are 7 columns, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Then here um, column 2, column 4, and column 6, they are having ones. So column 2, column 4, and column 6, so they have been brought front. Then see the row 4. So column 2, column 4, column 5, column 6, column 2, column 4, column 6, column 5. They have been underlined, they have been brought back. 2, 4, 6, 5. They have been brought back. So brought front. Similarly, we underline and bring it to front. Then finally, new column order becomes 1, 3, 7, 2, 4, 6, 5. So now we put the columns 1, 3, 7, 2, 4, 5, 4, 6, 5. So that is written, and the rows have been written, and you found out block diagonal structures. This is what we simply do. There is another method in the group technology that is used, that is known as the similarity coefficient methods. In the similarity coefficient methods, suppose this is the incidence matrix given. There are 10 components or 10 parts and 5 machines. Then similarity between um, two machines, similarity between two machines, that can be found out. That is what are the components that is processed in both the machines. So component 2 or part 2, part 3, part 4, part 9, and part 10, they are processed in both the machines. So processed in both the machines, that is 5 number of components are processed in both the machines, 5 divided by number of ones in the first row. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Then number of ones in the second row, second machine, 1, 2, 3, 4, 5, 5, minus number of um, ones in both the machines, that is subtracted. So that will give you the similarity coefficient. 0.556 is for similarity coefficient between machine 1 and machine 2. So similarly, for all the machines combinations you calculate. For machine 1, 2, it is 0.55. Similarly, for machine 1 and 3, it is 0.30. Machine 1 and 4, it is 0.67. Machine 1, 5, 0.70, like this. So select two machines, M2 and M4, which are having the highest similarity coefficient of 0.83 to form a first cell. Then next lower coefficient similarity between M1 and M5, that is 0.70, that will form the second cell. So you go on combining like this. So M2, M4 is 0.83. So that is one cell. Then M1, M5, that is another cell, that is 0.83. uh, 0.67 m1 m5, that is 0.7. So similarly, you go on lowering down the similarity coefficient and get a graph like this, and you take a threshold value of the similarity coefficient, then you get the what are the machine cells that can be found. What are the machine cells that can be found out. So this is what we do in the similarity coefficient method. Um, so this is the mathematical formulation of the similarity coefficient will be used to form the machine cells. Now sometimes, in spite of lot of um, lot of attempts, it is really difficult to get the block diagonal structures. So if the ones found apart from the block diagonal structures, then these are called exceptional elements. So these exceptional elements, uh, uh, exceptional elements that is to be treated properly in real, in actual field. So we look at here. So these are the block diagonal structures, and these ones, they do not belong to any block diagonal structures. These are the exceptional elements. Now sometimes we calculate the group efficiency. Group efficiency is calculated in this manner, and for this structure, group efficiency is found out to be 85%. Now, after looking at so many types of methods for group technology, machine cell formation, we found that here we have one in the cell entries. These cell entries of one makes some sort of basic or rudimentary cell formation problem. But when you used to solve these problems, big problems, industrial problems, it is really difficult to solve, and such type of heuristic methods, row, rank order clustering, and other methods, bound energy methods, they also find difficult to get proper solutions. So genetic algorithm sometimes it is used to solve such type of problems. Then I have told you that the if you use, it is nothing but what are the combination of the parts that is assigned to a cell, or combination of the machines that is assigned to the to a machine cell. That is what we do. So we can have a complete 1-0 type of incidence matrix, or some other types of also. Now here, what we do, suppose we want to produce two machine cells, and the machines we are having 1, 2, 3, 4, 5 machines we are having. So randomly generate generate the uh, randomly generate the population, then each chromosome will look like 2, 1, 2, 1, 2. That means we are finding out two cells. So here the machine 1 goes to cell 2, machine 2 goes to cell 1, machine 3 goes to cell 2, machine 4 goes to cell 1, machine 5 goes to cell 2. This type of things that we can do here. So once you do here in such type of things, then you can use the genetic algorithm. You can use the use as usual the uh, reproduction. Then you can use the is PMX or OX type crossover. Then use the position based mutation, like that you can use, and you can find out the machine cells, and the easily you can find out the machine cells. Now sometimes what happens, we are simply bothered about whether a part is visiting a machine or not. You are not bothering how much time it consumes or how much time it gives. So what is the workload of the machine cell that we have not taken care of? If you consider what is the workload that is being given to the machine cell and try to attempt the workload in all the machine cells should be more or less equal, it becomes a different type of group topology problem. So here, instead of 1-0 matrix, we use the what is the operation time of the of a of a part that is being processed on a machine. What is the processing time? So such type of data is known as ratio level or real value input data or real data. Okay, or ratio level data. So if you use the ratio level data, the objective is to balance the workload in the machine cells. That will the objective. Not only to improve the similarity of the machines, that is not the objective. The objective is to balance the workload. So, in doing so, we have one example is given, a machine part incidence matrix of size 10 into 5. Then this is an example problem, existing problem or benchmark problem. So now, for wherever one appears here, instead of the ones, we have given a real value data. We assume that is the processing time. So the processing time may be in hour, maybe in minute, or maybe in day. So our objective is that the workload on each machine cell should be uniform. So doing so, we can have so using genetic algorithm, we can have a output we can produce, that is a these are the machines, these are the parts. So machine part incidence matrix is there. So machine cells and the part family can be produced using genetic algorithm. So this is what the conversion score is given using the genetic algorithm. So this is how we can use genetic algorithm, a combinatorial version for for producing machine cell incidence, machine cell or the in cellular manufacturing. Then come to another type of problem that we come across, that is a flexible manufacturing system where we are concerned about the loading problem in flexible manufacturing system. So a flexible manufacturing system consists of a group of processing workstations interconnected by automated material handling and storage system and controlled by a distributed computer system. This is what the flexible manufacturing system. So these are the trends in manufacturing. That is the flexible manufacturing system where it lies CNC machines, then flexible manufacturing cells, then flexible manufacturing system, like that. This is the trend in manufacturing. I'm not going to the where it is applied or all these things, but what we are concerned more importantly is the loading problem. In many in machine loading in flexible manufacturing system, which is a costly system, we do um, do solve a loading problem, which is a planning problem, before machining or scheduling the jobs on the machines. We try to find out or do the plan of loading of the machines, whether these are possible or not. So this is a what a loading problem. So machine loading problem deals with the selecting a subset of jobs from a set of all the jobs to be manufactured and assigning their operations to the relevant machines in a given planning horizon with the operational and technological constraints in order to meet certain performance measures such as minimization of system unbalance or maximization of the throughput. This is what we do. So this is an example where we have given there are 8 jobs in a planning period. Now these jobs are produced. Job 1, the base size is 8. Job 2, base size is 2. Job 3, base size is 13. Job 4, base size is 3. And job 5, base size is 9, like this. This is the base size. Then the job 1 requires only one operation and the processing time is 18 and one tool slot will be required. In the CNC machines, tool slots will be there. So one tool slot will be required and it will use a machine number 3. Job 2, which has got base size of 9 and it has 3 operations, 1, 2, 3 operations, and the processing time for the first operation is 25, second operation 24, third operation 22. Then and tool slots required is 111, and operation 1 of job 2 that can be assigned to either machine 1 or machine 2. Job operation 2 can be assigned to machine 4 only. Operation 3 can be assigned to machine 2 only. But now, if this is what the flexible, you can load the job on, yeah, you can load the job on any machine. Now, if you look at the problems, there are 8 jobs and the number of possible operations So, so the total possible allocation will be look at this figure 104509440. So this is for a 8 job problem. These are the combinations that is required. So it is really a tough problem. So we have to find out the best possible loading sequence on the machine depending on the tool slot constraint and the time constraints in the planning period. So to solve such type of problems, we can go to different literature. So the mathematical formulation of this problem is given here. Throughput is the what is the output that we are getting from the uh, FMS system. So that is the throughput maximization. And here machine loading is not permitted. So accordingly the mathematics have been formulated. Then we have found out case 2 where the throughput is maximization but machine can be overloaded. And this is the system utilization maximization. Here throughput is not important. How to utilize the system. So system utilization maximization and machine overloading is not permitted. And this is the system utilization maximization, machine overloading is permitted. So and here the objective is utilization and the efficiency both is taken. Thereof machine overloading not permitted. So many permutation of different types of different types you can find out uh, different types of mathematical formulation and such type of problems can be solved using integer programming problems. If you are acquainted with the Lindo package, then you solve with the integer programming problem. But when the problem size becomes large, your um, conventional methods breaks down. So you have to search for a new method. So these problems can be solved using of course, genetic algorithm and other algorithms have been tried uh, in the past, but you can easily solve such type of problems using particle swarm optimization. A particle swarm optimization is nothing but the imitation of the behavior of the birds or the fish. Now, birds and the fish, they move in a swarm. We consider as birds are sitting on the trunk of tree, right? And they find a food source. What they do when they find a food source, the swarm of birds will rush together to the food source and they communicate in exchange the information among themselves to reach at the food source. So this is what they do. Now this has been imitated, and if you use the particle swarm optimization, it uses only two equations, that is the velocity and the position equation. Now consider the bird sitting on a tree. You can consider the bird is having, you can define a bird's position having three axes, x1, x2, x3, three axes or xyz. You can define a bird, the position of the bird. Now when they move towards the food source, they change their velocity. So in the x direction, x1 direction, x2 direction, and x3 direction, in all three directions, their velocity is being changed. So if there are three variables, we can think of the the coordinates x1, x2, x3 coordinate of the bird's position as three variables. If you consider multiple variables, you think of a multidimensional space. Then, so the bird, the bird change their velocity as they move. Velocity is being changed, and their position is also being changed. So the new velocity in iteration t of the bird I, her variable j or the dimension j equal to an inertia factor, that is Wt multiplied by previous velocity c1 and r1 tij xij c2 r2 gj, and in this case this r1 and r2, these are known as two parameters. So these parameter values will be 2. Okay, and sorry, C1 and C2 are two social and cognitive parameters. The values will be 2, and R1, R2 are random numbers between 0 to 1, and Pij is the personal best of a particular bird. Okay, now and in this you create a swarm, that is a population is being generated or solution, a set of solution is being generated, and each solution is updating themselves. So that is the personal best. So far they have achieved the best, that is the personal best, and among these swarm, one is the best, that is known as the global best or G best. So you update the velocity of any very of a bird or a particle using this velocity, and the positions are changed. The position values are operated like this. So it uses only these two equations. So this is the PSO algorithm. Initialize the parameters, initialize the population or the number of birds, find the permutation, evaluate, find the personal best, find the global best, and update the velocity, update the position, find permutation, evaluate. This is what we do. Now the thing is, how do we find? It is a continuous problem, but in the machine learning problem, we need the combination. What is the what is the combination of the parts that wish to be given, so that or loaded, so that we will meet some objective, that is either machine utilization that can be improved or system utilization can be improved, or throughput can be improved. Throughput is the number of units that is being produced in the planning period. That is the throughput that is can be improved. So to find out the job sequence or find out the what is the job that is to be loaded. Now, if the dimension a smallest position value method is used, smallest position value. So for a particle, these are the positions. Now 1, 2, 3, 4, 5, 6 jobs are there. Then this is the position values. So the sequence will be now the smallest position value will come in the first sequence. So 0.11, so it has come in the first sequence. Then next minimum is 0.32, so 6 comes next. Then next minimum is 0.45, so 4 comes next. Then 1.08, so 5 comes next. Similarly that. So these are the dimensions, and the next job sequence becomes using this shortest position value method 164532. That will the job sequence. So accordingly you can load. So you can using this a 10 benchmark problems of different size of the problem have been solved considering different cases. Case 1 throughput maximization, machine overloading not permitted. Case 2 throughput maximization, machine overloading permitted. Case 3. So for different cases have been solved, and these have been solved and compared with the existing results. Okay, existing results, and SU is the system utilization, TP is the throughput. So we are getting some comparable results using the swarm optimization. These Nagarjuna, Mahesh and Rajgopal, they have used a heuristic method. Srinivas et al. Have used another heuristic, and Sonakar and Tiwari have used a genetic algorithm. So we have compared the results of the swarm optimization with the existing results, and we found that superior results can be found out. So these are the solution methods that have been shown, and some other problems comparison is made with other solutions. Okay, other solutions. So we are getting some, and this is the number of iteration that we are getting. So we are getting a superior result for machine loading problem. So I shall show you a very interesting thing that we normally come across traveling salesman problem, which is used in many types of operations management problems like scheduling problem, vehicle routing problem. But the traveling salesman problem is the basic problem. Now, in the traveling salesman problem, what we do, a salesman starts from a city and makes a tour to different cities. So the idea is to find out the shortest distance or the shortest cost of the route that is to be found out. So such type of problems are commonly used in operations management, and I want to try to demonstrate with MATLAB how such type of problems is solved. Now using genetic algorithm. So here the number of cities are 8 cities are given 1, 2, 3, 4, 5, 6, and 6, 8. These are the coordinate of the city 1, xy coordinate of city 1, then xy coordinate of city 2, xy coordinate of city 3. These are given. So our object is to find out the best combination of the tour so that the distance traveled, Euclidean distance traveled will be minimized. So that is what we do. So these are the cities and the input is given, the city information, and we have taken population size of 500. Number of cities are 8. Then create the first population. Initially, randomly create a population. Okay, so we sort here, and the best route is found out to be 25416.873, and in this case, minimum distance will be 270.1872. 1872 minimum distance. So, and this is the best route we have found out. So such type of problems we normally come across, and if you understand the traveling salesman problem, which can also be solved using integer programming. Okay, this can also be solved using the integer programming. If you understand properly, then you can easily apply such type of concepts to many operations management problems. Remember, the most important thing is that how to map the continuous version of the algorithm with a combinatorial version. In most of the operation management problems, we will find combinatorial automation problems. So that mapping is really very, very important. So with this, I stop here. If you have any question, you can ask me. Of your own questions, if you are continuing any problem or any research issues, you can ask any question to me. Okay, not related to this discussion, but you can ask any question. Okay, hi, please.
Dear participants, please put your queries related to this session.
Hello.
Okay, thank you, sir.
Okay, I think no question is there. Okay, fine.
Thank you very much, sir. Dr.
Thank you very much.
S.S. Matra, sir. What is the concept of optimization? Difference between heuristics and meta heuristics, and how generic algorithm will be built. And he explained nicely the concept of group technology, what are the techniques in group technology, clustering process, and he highlighted the areas where you can apply these meta heuristics. And he has given brief the design using this meta heuristics. And he has highlighted as related with the use of MATLAB for the application of these operation management problems. Thank you very much, sir, for sharing your views and enlighten us related to the concept of these meta heuristics in operation management area. Thank you very much, sir. Hope you will have the fruitful interactions in coming future also. Thank you very much, sir.
Thank you very much. Okay.